Projective Geometry, Volume 1, by Oswald, Veblen, and John Wesley Young.
Chapter 7, Coordinate Systems in 2- and 3-Dimensional Forms. Section 72, Finite Spaces. It will be of interest at this point to emphasize again the generality of the theory which we are developing, since all the developments of this chapter are on the basis of assumptions A, E, and P only, and since these assumptions imply nothing regarding the number system of points on a line except that it be commutative, it follows that we may assume the points of a line, or indeed the elements of any one-dimensional form, to be in one-to-one reciprocal correspondence with the elements of any commutative number system. We may, moreover, study our geometry entirely by analytic methods. From this point of view, any point in the plane is simply a set of three numbers x1, x2, x3, it being understood that the sets x1, x2, x3, and kx1, kx2, kx3 are equivalent for all values of k in the number system, provided k is different from 0. Any line in the plane is the set of all these points which satisfy any equation of the form ux1 plus ux2 plus ux3 is equal to 0. The set of all lines being obtained by giving the coefficients, coordinates, u1, u2, u3, all possible values in the number system except 0, 0, 0, with the obvious agreement that u1, u2, u3, and ku1, ku2, ku3 represents the same line, for k not equal to 0. By letting the number system consist of all ordinary rational numbers, or all ordinary real numbers, or all ordinary complex numbers, we obtain, respectively, the analytic form of rational or real or complex projective geometry in the plane. All our theory thus far applies equally to each of these geometries, as well as to the geometry obtained by choosing as our number system any field whatever, any ordinary algebraic field, for example. In particular, we may also choose a finite field, i.e. one which contains only a finite number of elements. The simplest of these are the modular fields, the modulus being any prime number p. Footnote: a modular field with modulus p is obtained as follows. Two integers n, n prime, positive, negative, or 0, are said to be congruent modulo p, written n congruent n prime mod p, if the difference n minus n1 prime is divisible by p. Every number is then congruent to one and only one of the numbers 0, 1, 2, p minus 1. These numbers are taken as the elements of our field, and any number obtained from these by addition, subtraction, and multiplication, if not equal to one of these elements, is replaced by the element to which it is congruent. The modular field with modulus 5, for example, consists of the elements 0, 1, 2, 3, 4, and we have, as examples of addition, subtraction, and multiplication, 1 plus 3 is equal to 4, 2 plus 3 is equal to 0, since 5 is congruent to 0 mod 5. 1 minus 4 is equal to 2, 2 times 3 is equal to 1, etc. Furthermore, if A and B are any two elements of this field, A not equal to 0, there is a unique element x determined by the congruence AX congruent to B mod P. This element is defined as the quotient B divided by A. For the proof of this proposition, the reader may refer to any standard text on the theory of numbers. In the example discussed, we have, for example, 4 divided by 3 is equal to 3. If we consider, for example, the case p equal 2, our number system contains only the elements 0 and 1. There are then 7 points, which we will label A, B, C, D, E, F, G as follows. A equal to 0, 0, 1, B equal to 0, 1, 0, C equal to 1, 0, 0, D equal to 0, 1, 1, E equal to 1, 1, 0, F equal to 1, 1, 1, G equal to 1, 0, 1. The reader will readily verify that these 7 points are arranged in lines according to the table by column A, B, D, B, C, E, C, D, F, D, E, G, E, F, A, F, G, B, G, A, C, each column constituting a line. For example, the line x1 equal 0 clearly consist of the points 0, 0, 1 equal A, 0, 1, 0 equal B, and 0, 1, 1 equal D, these being the only points whose first coordinate is 0. We have labeled the points of this finite plane in such a way as to exhibit clearly its abstract identity with the system of triples used for illustrative purposes in the introduction, section 2. Footnote: for references and a further discussion of finite projective geometries, see a paper by O. Veblen and W. H. Bussey, Finite Projective Geometries, Transactions of the American Mathematical Society, Volume 7, 1906, pages 241 to 259. Also, a subsequent paper by O. Veblen, Collineations in a Finite Projective Geometry, Transactions of the American Mathematical Society, Volume 8, 1907, pages 266 to 268.
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renholt, with programming and illustration by Jim Renholt, 2019. Thank you for listening.